If you're a junior engineer, toilet ventilation is one of those topics that looks simple on a drawing but gets misunderstood all the time in real design. Because at first glance, it feels like an easy room, it's just a toilet. Put extract in, job done. But that is exactly why people get caught out. By the end of this video, you'll understand how toilet ventilation sits inside Approved Document F Volume 2, what actual rates the document gives, and what junior engineers should really be checking when they review toilet layouts. This video is based on Approved Document F Volume 2, so always check the full guidance and project-specific requirements before using it in live design work. The first thing to understand is that toilet ventilation is not just a fan selection exercise, it is an air movement and room function problem. You need to think about where the stale air is being extracted from how replacement air gets into the space, whether the room is likely to be used heavily, and whether the airflow route actually works in practice. Now let's get into the actual numbers, because that is where this becomes more useful. For offices, Approved Document F Volume 2 says that sanitary accommodation and bathrooms should have an intermittent air extract rate of 15 litres per second per shower or bath, 6 litres per second per WC pan or urinal. Those are the two numbers to remember first. So if you have 2 WCs, that is 12 litres per second, 3 WCs and 1 urinal. That is 24 litres per second, 2 showers. That is 30 litres per second. That makes the rule much easier to visualize. And the document also says something else that matters. Extract ventilators in sanitary accommodation should be capable of continuous operation if required. That is important because it tells you this is not always just a simple on-off fan arrangement. Depending on the building use and system strategy, the extract may need to operate continuously. That is the first junior engineer watch point. Do not just ask, is there extract? Also ask, what kind of extract operation is the design relying on? The second big point is that toilets do not work in isolation. If stale air is being extracted from the toilet, replacement air has to come from somewhere. That means you should be asking, is air being transferred from a corridor, lobby, or adjacent space? Is that transfer path actually realistic? Has the room been laid out in a way that allows the ventilation strategy to work properly? This is where toilet ventilation often gets missed in practice. The fan might be selected correctly. The rate might look fine on paper. But if the transfer air path is poor, the room can still underperform. That is why junior engineers should stop thinking only in terms of extract point shown, and start thinking in terms of airflow direction. A toilet should be a space where air is drawn towards it and then extracted out, not a space where stale air drifts back into adjacent occupied areas because the strategy is weak. Another thing that gets missed is that not all toilet spaces are the same. A single accessible toilet, a small office WC cluster, and a larger public washroom may all be labeled toilet on the drawing. But the way they behave in use can be very different. The more intensively used the space, the more important it becomes to think beyond just the bare minimum rate and ask whether the extract strategy is robust enough in practice. That is where better engineering judgment starts. So the simple takeaway from this video is this. For office-type buildings, the key numbers to remember are 15 litres per second per shower or bath, 6 litres per second per WC pan or urinal. But toilet ventilation is not just about hitting those numbers. It is also about making sure stale air is removed properly. Replacement air can actually get in, and the room works as part of the wider airflow strategy of the building. If you are a junior engineer, that one mindset shift will make your design reviews much stronger. If this helped, subscribe to The Lazy Engineer, because I'm breaking approved documents down into the real design questions junior engineers actually get stuck on.